Everyone, and welcome to this module on incompatibility equation for infinitesimal strain. There's something very important about this video. This is something I would like to mention here at the beginning. I don't know why the book bring forward this topic in here because I prefer to have this topic in chapter 5, the elastic solid. So not knowing this kind of, compatibility condition or this topic, it does not hurt your knowledge of continuum mechanics and, appreciating the strain and stress field, which we deal with in the next chapter. So if you feel that you may not have enough time to watch this video or understanding this may be somehow difficult for you, so you can skip this one. However, I do my best to make this topic quite easy, understandable, and I try to derive all the equations and try to be as precise and clear as possible so you can learn something new, which can be later used for your courses like elasticity, plate and shell theory, composites, and so many other courses. All right, so let's get us started. Uh, the topic, as I said, is most related to the elasticity field rather than continuum field, continuum mechanics. So I have to mention some preliminary topics in here, how we solve the problems in elasticity or in general. Uh, so to solve problems in elasticity, we have two approaches. In the first approach, which I use this black color for this one, we basically have the displacements. So we have a displacement, we have the displacement fields, and from the displacement fields, we are able to get strains. Uh, this is quite easy because we already draw a connection between the strain and displacement. And as I already said, we up until now we have discussed both the large as well as infinitesimal strains, but we haven't get into the detail of large deformation. We will do it in next modules. But let's write in here we have either large or infinitesimal strain, or maybe deformation is better. So I also put arrow here indicating that we are moving in this direction. So we have these strains, and from the constitutive law, we are able to draw a connection between the strain and stress. For example, you already had in your mechanics of material course that sigma is equal to a epsilon, where E is the Young's modulus here, not the infinitesimal strain tensor here. So E is the strain and sigma is the strain, the stress. So based on this, we can draw a connection between these two, between the strain and the stress. And from stress, we can calculate the forces. So for example, if you remember, we had sigma equal to F divided by A, right? The Cauchy strain tensor, which we will deal with in the next chapter, where it is better to write it in the limit format, like the limit of F over A when A goes to 0. But let's keep it this simple. Sigma is equal to stress is equal to force divided by the area. So based on this, you can get the forces. So this connection could also be linear or nonlinear. So linear or nonlinear. And I forgot these arrows in here. We're moving in this direction. Maybe it's better to put a triangle here. Okay. In second approach, so in approach 2, maybe I change this to another color so you can't confuse it with. All right. So in the second approach, we already have the forces. For example, the loads that are applied on your domain, for example, we have the forces. It is a distributed force or it is a concentrated force, for example. You have the moments, for example. And from here, we are able to calculate the stresses. From stresses, we can get to strain using constitutive law. And from strains, we can get to the displacement field. However, in this approach, approach 2, we have to make sure that the final displacement we get represents a continuum, a continuous domain. So suppose you have a field like this. This is a continuum. And you have a particle right over here. And I already mentioned, and can't emphasize more than this, that when we talk about a continuum, we mean a particle where it is surrounded by infinite number of particles. So remember this. This is only a schematic of an infinitesimal part of a continuum. So when we have the displacement field, so we know that, okay, we have a displacement field which is continuous. So it is, of course, differentiable. We get the strains, then we get the stress, then we get the forces. This is the first approach. And for example, your deformed shape could be something like this. Sorry. So this is the deformed shape. And this is the undeformed. This is from approach 1. In approach 2, you have to make sure that if you have something like an undeformed configuration like this, you have to make sure that your undeformed solution is also, I made a mistake in here. So the that your undeformed is also continuous. So you can't have something like this, for example. This is the deformed shape. Why you can't have something like this? Because you have, let me just show this by another color, because you have these discontinuities in here. These are the discontinuities that you have in your solution. So, possible answer from approach 2. So to guarantee that your solution is uh, basically represents a continuous domain or a continuum, you have to satisfy a set of equations. We will discuss this in this module. Okay, let's answer this question. Why compatibility equation? Sorry, compatibility equations. We, in elasticity, we make an important assumption. This assumption is basically a continuous domain or continuum. You're dealing with a continuum. Also, our displacement fields they should be single valued. Otherwise, you have different solutions to one problem. So, from, if you remember from infinitesimal strain tensor, we had, if you remember, it was E equal to half of del U plus del U transpose, which was basically equal to half of ui comma j. So it was the differentiation of ui with respect to capital xj plus uj comma I was this one. Here we derive, so from above equation, we get 6 equations, if we remember. So we had E11, E22, E12, and the rest. Maybe it's better to write all of them in here. 1, 2, 1, 3, 2, 3. However, we have 3 unknowns. unknowns or displacement. Which are, for example, U1, U2, U3, or UVW in some books. So therefore, we need to get, because here you see the number of equations is more, it is larger than the number of the unknowns. Therefore, there is a possibility of having a multi-value solution. Therefore, to get continuous single value, remember this is continue and this is single valued and single value solution displacements, we should or we need to satisfy compatibility equations. These are first found by Saint Venant. If you remember the name from your mechanics of materials, Saint Venant principle is a very important principle in the solution of elasticity problems and so many other analysis. All right, so now we understood why we need these compatibility equations, because we want to have continuous single valued displacement. We don't want to have something like this. We want to land in something, for example, if we move from approach 2, we need something like this. I also need to add something here. We need to get a displacement field which is continuous and also single valued. Therefore, I also like to add this in here, that we only need to satisfy this compatibility equations from approach 2. So if we start from approach 1, if we use approach 1 and we move from displacement field, we already satisfied this continuous single valued answer or the compatibility equation. Therefore, it should be noted that the strain compatibility equations are satisfied automatically when the strains are computed or maybe derived from a displacement field. This is approach 1. Thus, one need to verify the compatibility equations, only, it's better to say only when strains are derived from stress or stress strain, maybe constitutive law. All right. So with this in mind, let's get to see how we can get these compatibility equations. Deriving the compatibility equations. Deriving compatibility equations. All right. So for the infinitesimal strain, if you remember, we already wrote down that Eij is equal to half of Uij plus Uji. And let me just move this bit here. All right. So if I take the derivative of this with respect to xk and xl, capital X, remember? So I get something like Eij, comma, KL. So if you remember this, comma, it was the differentiation. So this become half of Uij KL plus Uji KL. Since these are all free indices, so I can manipulate them. So if I have Ij, comma, KL, I can differentiate KL. I can put KL in here, comma, Ij. The order of differentiation is not important. So if I have I in here, since I is the counterpart of K, so I put K in here. So I have IK, so I have J in here. I have IK, so the order of differentiation is not important. The only one is J and K. So I have J and L. So I have J and L in here. And then I have I and L. These are not counterparts, so I have to use J and L. So if I put J and L here, so I have J as a first, so I have I and K. However, the order of differentiation is not important. All right. So let me change the color of this as well as this one. So I have here E. So instead of I have to write K. Instead of J, I have to write L. So I can write K L I J is equal to half of U K J K L plus U J I K L. So instead of I have to write J L. Instead of K, I write I. Instead of L, I write K. So I have E. So instead of I have to write J. So it is J L I K is equal to half of U K is, I guess that I made a mistake in the above equation because these are the same. It's impossible. Let me just do this again. So I is K, so it is U, K, J is L, K is I, L is J, Lij plus U, L, It's K I J. All right, so again, I have this and I have to replace it with these indices. So I have to have IU, J, L, I, K plus U, L, J, I, K. Then I have E, I, K, J, L, which is equal to of U, I, K, J, L plus U, K, I, J, L. Let me see. They are different. I, K, J, K. Okay, so. All right, true. So then I have four equations here. All right. So now from here, I can write. So if you manipulate these with plus and minus, you get E I J comma KL plus E KL comma IJ minus E IK comma JL minus E IL comma IK is equal to 0. This is basically the Saint-Venant compatibility equation. This is the Saint-Venant compatibility equation. So if you see here, we have four indices for three indices. So the number of equation is 4, 3 to 4, which is 81 equations. But if you write these equations due to repetition, and some of them actually they already are fulfilled, so they become 0, for example. And if you do some manipulations like changing, like swapping between K and L, you finally get 6 equations. I'm not going into the details, so you can just program this in your programming codes and see that you finally get 6 equations. And if you write them down, you get these equations in the book from 316.7 to 316.12. These are the compatibility equations in Cartesian coordinate system. You have to remember this, that these are in Cartesian coordinate system. But basically, you can get them from the curl of infinitesimal strain in other coordinate system like spherical or cylindrical. These are basically the uh, compatibility equations. So to give you an idea of how this works, the book actually uh, gave us an example. So it said that suppose you had a solution and you got such displacement field. These displacement fields, are E11 equal to kx2 squared, and the rest are 0. So suppose you, uh, so maybe, uh, let's call this continuous displacement intuition. Let's say that this is a title. So suppose you have below, we have the infinitesimal strain component below from a strain relation. So we would like to check if such strains yield a continuous single valued displacement field. Let's check this out. So I write the solution in blue. So we have E11 is equal to kx2 squared is equal to partial derivative of u1 with respect to x1. So if I take this partial derivative and I take it to the other side and I write it like this, so I have kx2 squared, and I integrate over the domain, so what I get is something like u1, sorry, is equal to kx2 squared x1 plus a function, I call it f1 for example, which is dependent on x2 and x3. Why x2 and x3? Because if you differentiate this with this displacement field with respect to x1, you only get this value. Next, I have e22, which is equal to 0, is the partial derivative of u2 with respect to x2. Therefore, if I have u2 is equal to 0, partial derivative of x2, and I integrate, I get u2 is equal to, for example, f2, which is a function of x1 and x3. Because if you differentiate this with respect to x2, you get 0. And I also have e12, which is half of partial derivative of u1 with respect to x2 plus u2 with respect to x1 is equal to 0, which is equal to, so I differentiate this solution here with respect to x2, so I get 2k x2 squared x1, so maybe x1 x2, sorry, x2 plus partial derivative of f1 with respect to, sorry, is a function of x2 and x3 with respect to x2 plus partial derivative of f2 x1 x3 is a function of x1, so with respect to x1. So here, if you see, we have a function of x1 and x2, Here we have a function of x2 and x3, and here we have a function of x1 and x3. So we have an expression here, which is a function of x1, x2, x2, x3, and x1 and x3, and it is equal to 0. Also, although the trivial solution is 0, 0, 0 for all these, so this for all these terms. So this is 0, this is 0, this is 0, and all the displacements are 0. But for non-trivial solution, you can see that this does not exist. Therefore, we can say that these strain fields are incompatible. Therefore, this is somehow impossible. Therefore, the above strain tensor is incompatible. It can't give us a continuum or a continuous solution. For example, it becomes something like this, for example. So here you have discontinuities in your domain, for example. All right. So now let's get to another topic, which actually deals with the simply connected versus multiply connected domains. And here we would like to show that the incompatibility equation is basically the necessary and sufficient condition for the simply connected. However, it is only the necessary condition for the multiply connected domains. But let's see what are these. So if you have a domain in continuum, and this domain does not include any irregularity or discontinuity, or it's better to say hole, for example, we call this a simply connected domain. And this simply connected could be something like this, for example. But a multiply connected domain is basically include an irregularity, something like this. Or it may also include some other irregularities. These are the irregularities. These are the holes in here. Or in other words, if you have a simply connected domain and if you can shrink it to a point which also includes that domain, we can call this a simply connected domain. But if you have a multiply connected domain and you want to shrink it, you can't do this without embracing the whole. So if you shrink this, for example, shrink this domain, you have to shrink it to, for example, something like this, which actually embraces the holes or the irregularities. Therefore, this is called a multiply connected domain. So incompatibility equation is the necessary and sufficient condition for simply connected domains. Let's prove this. Okay. Or maybe I can write this with another color, because this is a statement. And maybe the proof in another color. All right. Okay, for the proof, we actually assume we have a domain where in this domain, which is a simply connected domain, you have a point in here which is displaced to point 2 in here. So you have a P0, for example, where it is basically moved to, or it is deformed or displaced to this point P in here. So you have an initial vector here where we call this U0, and you also have another vector in here where we call it, for example, UP. And for this, we have a path. So we have a path C in here. So this is the problem statement and all the hypotheses that we have. So in order to write the displacement, we can write in here ui at O, because this is u1, u2, u3, at O, sorry, at P, because here we are in P, and here it is P0, or we can simply call it O, right? So, or this is the origin. We put our origin in here, and we can call this point P0. So maybe I write here origin. This is O, and the point name is P0. It's better to write it here. So we place the origin O in P0. Okay, so I can write UI P, different components of displacement, is equal to UI O, so this is the displacement at the origin now, plus the displacement over this curve. So I have the integral of dui on this curve on C. So I can write uio plus this dui. I can write it as ui, partial derivative of ui, with respect to xj dxj on C. So if you remember this one, it was basically del u, the displacement gradient. So this was equal to uio plus, maybe I write it here, uio plus the integral of del u dxj on C. And if you remember, this del u was a combination. We could write it, we can write it as E plus W, the infinitesimal strain tensor, plus the rotation, or the rotation tensor, if you remember. So it is UIO plus the integral of, here we have EIJ plus WIJ dxj on C. So here we have this UIO, I expand this part, EIJ dxj C plus the integral of Wij dxj C. Now let's get rid of this Wij. So let us get rid of wi this integral, because I'd like to write this integral in another form. Okay, so we have this integral in here. Let's get rid of this. Okay, so I write this with another color. So if you remember the integration by parts, we had, for example, uv comma j, for example. It was u comma jv plus uv comma j. This is the integration by part. So using integration by parts, we can write this as, so we have wij, right? And then we have xj. So if we take this, if we differentiate this expression, or maybe I can just move it here. Perfect. So I have dwij xj plus, sorry, wij dxj. So you see here, I have this expression here. This is this one. So I have this expression here. So I can write wij dxj is equal to dwij xj whole minus dwij xj. All right, so if I integrate, then we integrate. So I have the integral of wij dxj is equal to the integral of this, which is wij xj, right? Because this is d, so it becomes itself, minus the integral of d of xj dwij, right? So this d is here. And remember here, we are doing this from p0 to p, where this p0 is basically in the origin, because we moved this origin to, the origin to p0. Next, I can write this wij xj from 0 to p, which I simply write it as this, minus xj. I can write this partial derivative of wij with respect to x k dx k, for example, from 0 to p, or simply I can write it as wij comma k dx k. All right. And it is from 0 to p, or I can write it as c, simply. Next, we know that the partial derivative of wij, because I want to now calculate this wij comma k, with respect to xk, or this wij jk, is what? You want to know what is it? So we know that wij is basically half of ui comma j minus uj comma I. This is the rotation tensor, if you remember. So if we do this, then wij comma k is nothing but half of ui comma jk minus uj comma ik. All right, so now we have this. wij comma k is equal to half of ui jk minus uj ik. So if I write this, it becomes something like this. I'd like to open it. So you have uj. This is second derivative of uj with respect to xj, then xk minus second partial derivative of uj with respect to xi, and then xk. So I like to add and subtract one other term from this. So I can say I write this with another color, plus half of second partial derivative of uk with respect to xj, xi, minus, again, I subtract this. So second partial derivative of uk with respect to xj, xi. So if I do this, so you see that I have, using other colors, maybe this one. All right, so I have here this uij and xj, xk in here. So I have j between this and this. And this xi is basically common between these two. So I can get these together. So I write half of, so first second partial derivative of uj with respect to xj, then xk, plus this term in here, second derivative of uk with respect to xj, xi, minus half of, now this one, use second partial derivative of uj with respect to xi, xk, plus second partial derivative of uk with respect to xj, xi. Perfect. So now I can rewrite this in additional notation in the list-manic format. So I can get out this partial derivative with respect to j of u j k plus u k I, which is this one, minus half of, half of partial derivative of xi. I can get this out, so I get uj comma k plus u k comma j. Perfect. Now what I have is half of partial derivative. What is this? This is, no, I made a mistake. This is supposed to be j. I guess that this is ui. This should be I. And this is I. This is I. All right, now it makes sense. So this is nothing but u I k u k I, or e I k minus half of partial derivative of, this is jk k comma a k comma j, this e j k, or in other words, it is half of, sorry, it is not the half of, it is basically, this half is already included, minus is equal to, this is eik comma j minus ejk comma I. All right, so now we can say that this Wijk, we have found it, we already found it, it's in here. So I write this as 2 as 1 and 2. We plug 2 in 1. So what we get is, let me write this by color. All right. So I get ui at p, is equal to ui at o plus, if I remember, wij xj. It was we were not in here. We were in here. So it is 1, maybe I can just get rid of this. This is 1. This is 1. This is 2. So we plug in first 2 in, 3 in 2, and then in 1, right? So I have this, then I remember I had an integral on curve eij dxj, because this is I, so this is supposed to be xj, plus this asymmetric part, which was this one, wijxj. So it was wijxj, and it was at point P, if you remember, minus this integral, which was this one, right? So it was, it had an xj, if I remember. Yes, it had an, yes, xj and dxk. So I had an xj, and then I had this eikj, this one in here, minus ejk I dxk. So now I have this xij, and then I have this. All right. So if you see in here, we have dxk, we have dxj, and here j is a dummy index. So I can write this as ui at o at the origin. It's the integral of eik dxk plus wij at p, or I can maybe shift this in here, wijp xjp plus this integral, because j is the dummy index, so I can replace it with k ik dxk minus this integral, see, xj eikj minus ejk I dxk. Now we have dxk and dxk, so I can write ui at origin plus wijp xjp plus the integral over c of eik minus xj eik comma j. This is comma not I, k, j minus e j k I dx k. All right. So now, if we can show that this integral, which is on the curve C, it is independent of this path or this curve C, we can show that this is an exact differential. And using the Stokes theorem, we can say that the integral here is independent of the path C. and it's only dependent on the point, the last point. So it is not important which path you take, it is path dependent, path independent. So to get a unique displacement field, the above integral on curve or on path C should be independent of the path we take. In mathematics, we call this integral exact differential. And using Stokes theorem, remember here that we are dealing with a simply connected domain only for a simply connected domain. Here, the Stokes theorem only holds for a simply connected domain. The integral is path independent. So if I have the integral, if I copy this, and paste it here. So we have this integral in here. We can show that if this is basically equal to something like uik, because this is uik and here j is the DOM index, so what you get is basically something based on I and k. This is uik. We can show that uik, if we differentiate this with L, this is equal to u, I, L, and k. So this k and L, we can swap them. So if I do this, so what I get is eik minus exj eik. So let me just do this at the same time. So I have ik L minus x. So I have xj. So if I take the derivative of this with respect, because here we have a product of two things in here. So I have xj with respect to L e I k j minus e j k I. I take this down. This here. Then I have, so I have the differentiation of this with respect to L. Then I have times this one. Then I have this one times the differential of this with respect to L. Minus xj e I k JL minus EJKIL is equal to, here I have to swap I and L. So I have E ILK minus X. Here is J K E ILJ minus E J L I minus XJ E I L J K minus E J L I K. And remember here that this XJL, it can be only available when J is equal to L. Otherwise, it is unavailable. For example, if you have something like J is 1 and L is, for example, 2, so you have, for example, something like UX1, for example, U1, with respect to, it is X1 with respect to L is 2, for example, X2. This is 0. But if J and L are equal, so this becomes 1. Therefore, we replace it with JL, and this one can be replaced by del JK. All right. So I can further simplify this by EIK L minus. J is equal to L. So J is equal to L. I have EIK L minus E. J is equal to L, L, K, I minus XJ. The rest of the terms in here, JL minus E, JK, I is equal to, here I have E, I, L, K minus, here J is equal to K, E, I, L, K minus E, J is equal to K, L, I minus the rest. XJ is E, I, L, J, K minus E, J, L, I, K. All right. So if I see in here, I can simply get rid of this term and this term, because if I swap K and L, they are equal to each other. This is also the same in here. K and L, K and L. This is also the same in here. I have LK, I have LK, KL. I can get rid of this. So I only have these terms in here. So I have minus XJ EIKJL minus EJKI minus becomes plus XJ. I take everything to the left-hand side. EJLIK is equal to 0. So finally, I have XJ, these are positive, EILJK minus EJLIK minus EIKJL plus EJKI. I missed something in here. So I have IJ. This is L. So I differentiated L. I is equal to 0. This can't be 0, therefore this is 0. So copy and paste it here. This is equal to 0. And now we showed that basically for a simply connected domain, The incompatibility equation is the sufficient and, let me just bring this statement, is the necessary and sufficient condition. So now we're going to get to the multiply connected domain. For multiply connected domain, let me just bring it down a bit and draw, sorry, and draw a line in here. All right. So for multiply connected domains, we basically have a domain like this. This is the whole, or the irregularity. You can think of it as a whole. So for this one, we have to start from one side and then go around the irregularity and then get back to it on another curve. So we have point A, this is our starting point, point B, this is in this direction, the counterclockwise direction. B goes to C, C goes to D, and then goes to A. And here, remember that the integral from A to B is basically minus, is equal to the minus of integral of C to D. This is the direction. All right. Therefore, we can say that the integral from A to B plus the integral from C to D is 0. And also here, the integral from B to C is equal to the minus. If you see here, we have counterclockwise, here is clockwise. The integral from D to A. Therefore, for a multiply connected domain, two integrals should be 0. The integral of dui should be equal to 0 on the irregularity, because here we are moving around the irregularity. This is whole 1, for example, maybe whole, simply whole. And the rotations are also should be 0. Wi on whole should be 0. Or suppose you have a domain where you have infinite number of wholes, like 1, 2, 3, 4, and 5. These are whole, and this is your domain. So for this, the integral of dui should be 0 on each curve, on each CNE here. And here, n is 1, 2, 3. Also, dwi should be 0 on Cn, where n is 1, 2, 3, and whatever. And this recaps the topic or our discussion on compatibility equations. As I already mentioned, you do not need to understand all the things in here, because you will elaborate on these topics in courses like elasticity and similar courses like advanced mechanics of materials. But the book brought this topic, and I found it useful to explain uh, most of the ins and outs of the incompatibility equation, where it comes from, where it originates, why we need the incompatibility equation, and we also proved mm, the necessity and the sufficiency of incompatibility equations for the multiply connected, as well as for the simply connected. And also we showed that for the multiply connected domain, this incompatibility equation is uh, only a necessary only a necessary condition. So I also write this in here for multiply connected domains. The incompatibility equation is only necessary but not sufficient. So these are the integrals where we call them Cesaro integrals. So basically, Cesaro proved that for a multiply connected domain, you also need to fulfill these two integrals. And to give you an idea of a multiply connected, think of a cylinder like this. So there is a hole in here. Uh, this is a multiply connected domain. In reality, I mean. Uh, Also, Cesaro integrals should be zero on irregularities or discontinuities. All right. Uh, if you want to study more about these scissor integrals and you want to understand more about this topic, I refer you to a book in the description, so you can read and study more about these topics.